Hello everyone, hope you all are keeping well, and I'm going to start today's session, that is session number 3, and here we are going to discuss about control charts. So if you can remember in the last few sessions, we discussed why statistical quality control is important and how we use statistical quality control tools in order to evaluate your process, right? And what are the variations, what are the causes that you can find out through the statistical quality control and so on. So today we are going to discuss about the control chart. So if you can remember, in the last session, I showed a control chart to you. So in the control chart, you have 3 lines. That is the control line, upper control line, and the lower control line. So in that case, you have these 3 control lines, and I told you in order to find whether the process is in control or out of control, we will discuss in the coming up sessions. So when it comes to control charts, this was introduced by Swartz, and there are so many different types of control charts. So basically the control charts, you can divide control charts into 2 subcategories. That is, you have variable control charts, and then you have attribute control charts. So what are these variable control charts and what are these attribute control charts? So when it comes to variable control chart, in order to calculate the target value and its variation, you consider a numerical, or in other words, a quantitative variable. For an example, it can be the waist size of your garment, or it can be the length, or it can be the lifetime of a bulb, right? So likewise, if you are taking a quantitative measurement in order to evaluate the variable, we call it as the variable control chart. And in the other hand, when it comes to attribute control charts, attribute control chart means you are considering an attribute, a nominal scale variable, when you are considering the target value. Right, so it can be good or bad, or it can be yes or no. For an example, if you have a lot, you can count the number of defective items in the lot in order to construct your control chart. So in that case, we call it as a attribute control chart. Right, so when it comes to the design stage, when designing a control chart, there are some important things. Actually, there are 3 important points. One is the selection of the sample size. Right, so if you are going to inspect, or if you are going to check the quality of your process with the use of a control chart, the first thing is you have to decide the sample size of your process, right? How we are going to take the sample size, right? And then design of control limits. So when it comes to design of control limits also, there are so many variations. So that is also you have to decide how we are going to design the control limits. And then the frequency of sampling. Right, that is, if you are going to take samples from your lot, what is the frequency? That is, if the sample size is 25, how often you are going to take samples from your lot? Is it daily, or is it monthly, or is it 1 times per day, 2 times per day? Likewise, you have to decide the frequency. So that is, you have to decide the sample size and the control limits and the frequency of sampling when you are constructing the control charts, right? And then there are some issues related to this designing of control charts. One issue is the cost of sampling. right? Because we know when it comes to sampling, even when we are conducting a census, right? Sampling, for sampling you have, it's something bit expensive, so there is a cost associated with sampling. So the cost is a problem when it comes to sampling. And the other thing is losses from allowing defective product to be produced. Sometimes even though when we do sampling, we will not be able to find out the defective items, because sometimes our sample may consist with only non-defective. So in that case, we are allowing the defective products to be produced. So that will become a loss to the company eventually, right? So that is also a disadvantage of designing these control charts. And the cost of investigating out of control signals that are really false alarms. So sometimes when we use the control charts, with the use of the control chart, we say our process is out of control, but actually the process is in control. So this may happen due to an error of the control limits. If we have not specified our control limits correctly, we may end up with false conclusions. So that is also a disadvantage of designing these control charts. But if you check the quality control field, the control charts are so very popular in the statistical quality control field. So one thing is why they are so popular, that is it is a proven technique to improve the productivity, because the statistical quality control, in the statistical quality control field, it is very easy to use these control charts and it's very easy to understand them. So you can easily, with the use of these control charts, you can easily improve the quality of your process through continuous monitoring, and with that you can improve the productivity. So because of that, in the quality control field, the control charts are so popular. And also with the use of control chart, you can easily defect the prevention, right? And also you can provide the diagnostic information. That is, with the use of the control chart, you can easily find out whether your process is in control or out of control. So if it is out of control, that is, we are sure that there are some assignable causes due to this out of control. Then we can find out what are those causes. So to find out those causes, the control charts is the one which gives us the hint that our process is in out of control, right? So it provides diagnostic information. So that is why these control charts are very, very popular in the field. And then when it comes to control charts, if you take this improving productivity, why they improve productivity with the use of control charts, these are the reasons. That is, it reduces scrap and rework. So when it is when we use the control chart, since we are going to maintain the quality in a high level, it will reduce the scrap and rework. So when you reduce the scrap and rework, it will anyway increase the productivity. So when you reduce the scrap and rework, in other words, it will decrease the cost, right? And then the production capacity also increases with the use of these control charts, right? So because of all these reasons, in the field, control charts are very, very popular. So when it comes to control charts, so this average run length, which is denoted by ARL, that is very, very popular. right? So if you are planning to study in the quality control field, or if you are planning to do your higher studies in the field of quality control, or maybe you are planning to do your final year thesis, in this case this topic is very, very important. That is the average run length, which is denoted by ARL. So the average run length means average number of points that must be plotted before a point indicates an out of control condition. That is, when you are checking your process with the use of a control chart, when you are checking whether the process is in control or out of control, what you have to do is, when the process is in control or out of control with the use of the control chart, ARL means how many samples on average you have to take to get an out of control signal from your control chart. Right? So that is when your process is in control, on average how many samples you have to take to get an out of control signal. Right? So that is the meaning of average run length. So if the process is stable and uncorrelated, right, we calculate the average run length using 1 over P, where P is the probability, that is any point exceeds the control limit. So if you know the probability of exceeding any point from their control limits, you can calculate that probability, and 1 over P will give you the average run length, that is the number on average how many number of samples that you have to take in order to detect an out of control signal from your process, right? And when your process is in control and when you calculate this average run length, we denote it by ARL 0, or you can tell it as ARL note, right? So that is very important when you are using your quality control charts. This you can calculate ARL and find out the number of samples that you want to get on average, that you want to get an out of control signal. All right, so we'll just have a look on example. Consider a process with mean 50 and standard deviation 12. Right? So construct 3 sigma control charts for the sample mean, and when the sample size is equal to 4 and sample size is equal to 60. And also you have to recalculate the ARL for the same process when mean is equal to 50 and 56, and when mean is equal to 62. So how you are going to do this, right? So if you have a look on this thing, okay. So basically when you are constructing a control chart, it looks something similar to this diagram. That is, you will have 3 lines. We know the middle line is equal to the control limit or the central limit, and you have a line which is above the middle line, that is the upper control limit, right? And then you have another line which is below the control line, that is the lower control limit. So when it comes to the control line or the central limit, you take it as mu. So in this case also they have given you the mu value is equal to, the mean value is equal to 50. So when you are constructing the control chart, right, you can take the mu value is equal to 50, right? So that now you can take, since the mu value is equal to 50, that indicates the control line you have to plot with the value 50. Now you know the control lines, or the central line value. And then now you have to construct the upper control limit and the lower control limit. So if you just have a look on the question, it's asking you to construct 3 sigma control chart. So in 3 sigma control chart, that means when you constructing the 3 sigma control chart, you have to use this equation, that is mu plus 3 times sigma, right? So if they ask you to calculate 6 sigma control chart, what you have to do is, that is mu plus 6 sigma. Now in this case it's about 3 sigma, so you can go with this equation. So the upper control limit equation will be mu plus 3 sigma, lower control limit equation would be mu minus 3 sigma. And if you have a look again at the question, you have to construct 3 sigma control charts for sample mean, right? When the sample size is equal to 4 and 60, right? So that is also something you have to consider. Now here, if you first consider the case where the sample size is equal to 4, so the sample size is equal to 4, right? And here you have to calculate for sample mean. That is very important. So we know the sample mean is denoted by x bar, right? So if the sample mean is denoted by x bar, then the next question is, what is the sample standard deviation, right? So we know sample standard deviation is equal to, you can take x bar divide by root n, right? That is the square root of n. So this is the equation that you have to use to calculate the sample standard deviation. So in that case, when you are calculating the UCL, the equation is mu plus 3 times sigma. But here now, this sigma you have to replace with what? Sorry, here not x bar. Here the sample standard deviation for the sample mean is equal to sigma divide by root n. So when you are calculating the upper control limit, what you have to do is, you have to take the upper control limit equation, that is mu plus 3 sigma, and the sigma you have to replace by the new sigma value, that is the sigma over square root n, since it is the equation for calculating the sample standard deviation when you consider sample mean, right? So in this case, if you consider the values, now we know the mu value is given, that is 50, right? So the mu value is given, that is mu value is given, that is 50 plus 3 sigma control limit. So you take 3 multiplied by sigma is given as 12, divide by the first sample size that we have to consider, that is equal to 4. So you have to take the square root of 4, that which is equal to 2. So if you simplify these values, you will ended up with 59. Right? That is, the UCL value is 59. So using the same equation, you can calculate the LCL value as well. So the LCL value is, you can take, that is the same equation you can take, but you have the minus sign here, that is LCL is equal to mu minus 3 into sigma over square root n. So if I just substitute the values here, mu value is 50 minus 3 times sigma is 12 divided by square root of 4 since n is 4. So that is, you have the value as 32. And the UCL value, I have done a small mistake. The UCL value should be equal to 68, and when you simplify this equation, and the LCL value is equal to 32, right? So now we are having the values of our control chart. That is, the control limit is equal to 50, and we have the upper control limit that is equal to 68, and we have the lower control limit which is equal to 32, right? So you can draw these three lines where this value is equal to 68 and this value is equal to 50 and this value is equal to 32. So basically this will be your control chart, right? And if you do the same calculation by changing the sample size, because in the question, if you check the question, you have to construct the control charts when sample size is equal to 4 and when sample size is equal to 60. Right? In that case, what you have to do is, now we have to consider the case where sample size is equal to 16. So, but since the mean value remains the same, so the central limit or the central line would be the same value, that is equal to 50. And when you take the upper control limit, so the mu value is 50 into 50 plus 3 into sigma value is 12 divided by, here you have to take now square root of 60, that is 4. Right? So in that case, if you simplify this, you will find 50 value as 59, and when you take the lower control limit, you have 50 plus 3 times 50 minus 3 times 12 divided by square root of 16. So if you simplify this, you will get the lower control limit as 41. Right? So you can construct the control charts with these two values. Now the problem is, how are you going to calculate the ARL value? Or in other words, how are you going to calculate the average run length using your control chart? So I told you the average run length means the on average how many samples you have to take in order to get an out of control signal, right? So in that case, what you have to do is, we know when you calculate ARL, so when you calculate ARL, the average run length, this is equal to 1 over P, where P is the probability of getting an out of control signal or probability of exceeding any point beyond the control limits, right? So this is exceeding any point beyond the control limits. right? So in that case, if you look at your control chart, right, if you can find a control limit somewhere, let's say right, if you can find a control, if you can find a value somewhere here or somewhere, if you can find a value somewhere here, right, you can see I have drawn two circles. One circle is beyond the upper control limit and the other circle is below the lower control limit. So if you can find values which is above the upper control limit or below the lower control limit, that is your process is not in control. So when you look at your control chart, in order to conclude that your process is in control, you need to have all the points within these upper control and lower control limits. Right, if they are not within this band, then we consider the process is in out of control. So if you want to calculate the probability of exceeding any point these two control limits, that is basically you have to find the probability of getting a point which is higher than the upper control limit or which is lower than the lower control limit. So if you consider our first case, in that case our upper control limit value is 68, lower control value is 32. So if you are going to find this probability, that is basically what you have to find is, we have to find the probability that the mean value, we'll take it as x bar, it can be greater than 68 or plus the probability of getting the mean value, the probability of getting the mean value less than the lower control limit. Or in other words, it's 32 as per our first example. So this one you can calculate the probability because we know the mean value is 50 and we know the standard deviations as well. Now for an example, if you calculate the first one, that is you can calculate this probability. You can convert this into the Z score. So you have Z greater than, you have 68 minus mu value is equal to 50 and the whole thing you have to divide by the standard deviation. So since we are considering the sample mean, the standard deviation value is 12 over square root n. So n is 4, you can take it as square root 4. So this probability you can calculate, or else you have the probability of receiving any point less than the lower control limit, that is x bar less than 32. So if you convert this into Z score, Z less than, from 32 you have to subtract 50 and divide it by the standard deviation. So standard deviation is 12 over square root 4, right? So this is the probability that you have to calculate. So using standard normal table, you can calculate this probability, or what you can do is, actually this probability is equal to 1 minus the probability of receiving any point within these two limits. That is, if you can find any point between this 32, that is if you can find x bar between 32 and 68, that is your process is in control. And since we are considering the complement of that, you can calculate this probability by 1 minus probability where the process is in control, that is all the points are in between 32 and 68. So again, to calculate this probability, what you can do is you can take standard normal table and calculate the probability, first you can convert these numbers into z-score. That is 32 minus 50 divided by the standard deviation, that is 12 divided by square root 4, right? And then you have less than z, you have 68 minus 50 divided by, here you have 12 divided by square root 4. So when you simplify this, you will get this one is equal to 1 minus probability minus 3 less than z less than plus 3. So this probability, if you read from standard normal table, that is equal to 0.9973. So that is, you will get this probability as 0.0027. Right? So this is the probability of receiving an out of control signal with the use of your control chart. Right? But still we are interested in ARL. So ARL is equal to 1 over this probability. Right? So in that case, what you have to do is, now our probability is equal to 0.0027. So when you calculate 1 over 0.0027, you will receive, that is nearly 370.39. Right? This is the ARL value. That is on average, if you take to receive an out of control signal, you have to at least take 370 samples from your process. Right? That is the meaning of this. Okay? And the important thing is, if you reconsider, if you do the calculation if you find out the ARL for the second set of values, that is, here we have changed our sample size. When sample size is 16, you can recalculate the ARL value. Right? You will see when you calculate the ARL value when the sample size is 16, you will end up with the same ARL value. Right? So that is for your homework. You can calculate for your homework, you can calculate the ARL value. To the following process, you will see you will get the same result. So that is an important point. That is because ARL is not depending on the sample size you take. Right? So that is a very important point. But if you look at the next question, you have to do the same calculation by changing the mean. Right? So if you change the mean from 50 to 56 and 56 to 62, then in that case, you will see, you will get different value for ARL. Right? So that is, you can just check at home by calculating. When the mean value is equal to, let's say, 56, you will find the ARL value is equal to 43.8. Right? That is on average, you have to at least take 44 samples in order to detect an out of control signal from your from the control chart. Right? So you can see your average run length is depending. It has changed with the mean value. It's depending on the mean, but it's not depending on the sample size. So that is something very important you have to remember. Okay, so actually what we do is now with the use of the control chart, what we do is we plot all these lines and we are monitoring our process until we get an out of control signal, right? That is, in other words, it has the characteristics. It's not actually a symmetric process because it has the characteristics of a geometric distribution, because we are waiting if when we observe a point, if it is within the upper control and lower control limit, that you can take as a failure because it's in control. What we are interested is we want to find out of control signal, right? So likewise we check whether the process is in control. If it is out of control, then we detect it. So we consider out of control as a success. So we are keep on doing this process. We are continuing this process until we get out of control signal. So it's like a geometric distribution, right? So the average run length, if you take this average run length, it's not a symmetric distribution because it has the characteristics of the geometric distribution, right? So if I go back to the lecture, so the average run length, it can be used to decide sample size and the sample interval, because when you calculate, now we saw with the example, when you calculate the average run length, we can get an idea how many samples that you have to take in order to detect an out of control signal. So we can use it to decide the sample size and the sample interval. So as I told you, it's not a symmetric distribution, right? So in this case, sometimes when it comes to this average run length, in field of quality control, we have defined another thing which is known as average time to signal. That is how long you have to wait by monitoring your process in order to get a out of control signal. So in out of control, in average run length, you get the average number of samples you have to get an out of control signal. In average time to signal, it gives you the average time, how long you have to look at your process control chart to get an out of control signal. So the average time to signal is calculated using this formula. That is, first you have to take average run length, then you have to multiply that by h. So h is if samples are taken at fixed intervals of time that are h hours apart. So that is, the time interval is denoted by h. That is, for an example, if you are taking samples in every 2 hours, right, from your production, h is equal to 2. So the average time to signal you can calculate using this formula, right? So when we observe control charts, you will see sometimes when you get points beyond your control limits, we say our control charts are out of control, right? So when it's out of control means sometimes it can be only one point which is above or below the control limits, right? That is, one or more points. If one or more points outside the control limits, we call it the control chart is out of control. And sometimes if you can observe some non-random pattern behaviors, right, even all the points are within control limits, but sometimes you can see some patterns. It's not random. So in that case also you can consider that our process is not in control. It's out of control, right? So what are these non-random pattern behaviors? That is, sometimes if more points can be above or below the central line, right? So there is a pattern, or a substantial number of consecutive observations form an increasing or decreasing sequence. So again, that can be a non-random pattern behavior. Or you have higher run lengths, and if you can see cyclic patterns. So I will, in the next lecture, I will show you some of the examples for these non-random behaviors. So in all of these cases, you can identify that your process is not in control, right? So these are the examples. That is 1 point out of the 3 sigma control limit. Then we can conclude our process is out of control. 2 out of 3 consecutive points beyond the 2 sigma warning limits, or 4 out of 5 consecutive points beyond 1 sigma from the central line, 8 consecutive points on one side of the central line, right? So in all these cases, we will see the diagrams in next slide. So what I want to tell you is, by basically looking at the graph, if all the points are within the control limits only, you cannot conclude that the process is in control. You have to check whether all the points are within the UCL and LCL, as well as whether they are indicating a random behavior. If not, the process is out of control, right? So I hope you get an idea about how to use the control charts and how to construct a basic control chart and how to calculate the average run length. So in our next lecture, we will discuss about these random behaviors of control charts and more calculations, how to construct the control charts and how to use them in your in the statistical quality control field in order to improve the quality of your process. Thank you.